So our goal today is to give you some more examples of how to graph the rational functions. I know the process is long, so we went really thoroughly through one example in our last set of notes. Today we're going to do 2 examples, again, very thoroughly. And then in our 3rd set of notes this week, we'll address what if the asymptote is not horizontal. Okay. So for this part B right here is what we're going to look at first. And it looks like it's been factored for us. Okay. But then you'd want to work on factoring the denominator if you can. Pause the video so you can figure out if you need, if you know how to factor it, then check. So here's what I would get if I factored it. Okay. So again, we're going to make this list of information. So we have asymptotes, intercepts, and holes are the information that we're looking for. So our asymptote categories, we have vertical ones, and then horizontal and oblique. You kind of had one or the other. You might have holes, and then x-intercepts and y-intercepts. So holes, I'm going to write none. We didn't have any factors that cancel out. Okay. And then for horizontal and oblique asymptotes, remember you can't have both, it's one or the other. So when I look at our problem, they have the same degree. If this was multiplied out up here, it'd be 3x squared minus 3x. The numerator and denominator have the same degree, which means there is a horizontal asymptote. And it will be at y equals a number, and that number is determined by these lead coefficients. So in this case, it would be 3 over 2. Okay. For my vertical asymptotes, I'm going to set the denominator equal to 0. So I'm already going to use it in its factored form. So when those 2 factors can be set equal to 0, with one of them, if I solved it, I'd subtract 1 and divide by 2. I'd get negative 1/2. Then I'd get 3. So I have 2 vertical asymptotes, one at negative 1/2 and one at 3. For my x-intercepts, I'm going to set the y value equal to 0. And then remember how we solved for this. We decided to multiply both sides of the equation by those denominator factors to get them to cancel out. That worked out nicely on this side to cancel them out and just leave the numerator. And on the other side, it works out nicely too, because no matter how crazy all this stuff is, it's multiplying with 0, and anything times 0 leaves us with 0. So we get 2 factors here. One would leave us with an x value of 0, the other with an x value of 1. So we have 2 x-intercepts, 0, 0, and 1, 0. And then finally our y-intercept, we're going to take the equation any form that you want and plug in 0 for x. Just make sure you do the arithmetic right. So in this case, I get 0 in the numerator, 2 times 0 plus 1, and then 1 times negative 3 in the denominator. So 0 over negative 3, which is 0. That's my y-intercept. So we're going to go ahead and put all of this information on your graph. So remember, your vertical asymptote is literally splitting your graph into separate branches. So we have one here at negative 1/2 and one here at 3. And our horizontal asymptote is not splitting up our graph in any way. We're literally just using it to know that the ends should follow this horizontal line. So remember, they can cross it all through the graph. It's just really important that they follow it here at the ends. Okay. Then we have x-intercepts at 0, 0 and at 0, 1. Or sorry, at 1, 0, excuse me, and a y-intercept at 0, 0. So that is all graphed on there. And this graph has a lot of sections for us to analyze, just like the last one did. So remember how we did this analysis. We're basically making ourselves a small version of the x-axis. And we're splitting it up by places that we see vertical asymptotes and intercepts. So in this case, that's at negative 1/2, 0, 1, and 3. And we're going to use this as kind of sections of x value numbers that we're going to plug in and test in this equation. Okay, and this time our equation is 3 times x and times x minus 1. And then in the denominator, a 2x plus 1. And then an x minus 3. So I'm going to plug something in. I'm going to try something in this section, which would be an x value smaller than -1/2. So let's say I try -10. So I'm thinking about -10 being in all of these spots. And that gives me something that looks like, okay, remember the 3 will always be positive. This says -10, so that's negative. And -10 minus 1 is negative. In the denominator, 2 times -10 is -20, plus 1 will still be a negative, and -10 minus 3 will be a negative. So look at what we have going on here. The multiplication here, a positive times a negative, then times another negative would be positive. Here, a negative times a negative would be positive, and a positive divided by a positive will be positive. Then I'm going to try between -1/2 and 0, so that kind of sucks, but I'll pick something like -0.2. So I'm going to have 3 times -0.2 times -0.2 minus 1, 2 times -0.2 plus 1, and -0.2 minus 3. So the 3 is always positive, -0.2 is negative, -0.2 minus 1 is still negative. 2 times -0.2 is -0.4, plus 1 would actually be a positive, and -0.2 minus 3 will be a negative. So in the numerator, a positive times a negative times another negative will be positive. In the denominator, a positive times a negative will be negative, and a positive divided by a negative would end up being negative. Okay. I'm going to try it again, and this time I'm looking to plug a number that's between 0 and 1. So I'm going to try positive 0.5. So I'm going to write this out for you guys, and then I'll go through it. All right, so let's see what happens if we're thinking about having 0.5 in there. 3 is positive, 0.5 is positive. 0.5 minus 1 is negative. 2 times 0.5 is 1 plus 1 is a positive, and 0.5 minus 3 is a negative. So in the numerator, a positive times a negative would be negative. A positive times a negative in the denominator would make a negative. And overall, a negative divided by a negative is positive. So this will be positive. Okay. Next, I'm going to pick a number between 1 and 3. So I'm going to pick 2. Some of you are like, why are you writing out all these steps? Others of you still need the steps. So just, write out what you have to write out. If you get it right one way, don't just try to do another way just to look faster or something. Make sure you're being thorough. So 3 is always positive, 2 is a positive, and 2 minus 1 will be positive. 2 times 2 is 4 plus 1 will be a positive. 2 minus 3 will be a negative. So all these positives make a positive. Positive times a negative will make a negative. A positive divided by a negative will be negative. And last but not least, I need to plug in a number bigger than 3. So let's say I pick 5. So 3 is positive, 5 is positive, 5 minus 1 is positive. 2 times 5 is 10, plus 1 is positive, and 5 minus 3 is positive. So you'll have a positive in the numerator and in the denominator, and the result will be positive. Okay. So let's remember what that means to our graph. I'm going to keep doing this highlighting. If it helps you, please do the highlighting on your scratch paper too, if it helps you decide where to graph things. So smaller than -1/2 means positive x's. Now notice that can still be below or above the asymptote, but we can't go below the x-axis. Then in between that asymptote and that intercept, it's negative. So this graph should be graphed somewhere down here. Between the two intercepts, it's positive. So any points I plot between them, the graph should exist up here. Between that intercept, so between 1 and 3, we got a negative. So all those points should be below the x-axis. And then after 3, we have a positive. So these points should be here. So now I have to make those sketches of what's happening. So remember our hints. We're really trying to use the asymptotes to help us. We know when we get close to the vertical asymptote, we're either going up or down. So every side of that vertical asymptote, I'm trying to think about which of these choices would be most likely, and look where your highlighting is. So first on this left side of this first asymptote, I would have to graph here, not down here. But on the other side, it would have to be down here, not up here. This next one would have to be down here. I'm just following where the highlighting is telling me, okay? So in this first section, as I go to graph over here, I have this guideline that I figured out has to be up here instead of down here. And then remember, this horizontal asymptote is here for the ends of the graph. I need to start looking like 1.5 over here. So I'm just going to connect these two behaviors with some sort of curve. We're just sketching, okay? On the other side of the asymptote, I already know it would have to be down here instead of up there because the highlighting, and I know that this is my next divider and it's an intercept. It's a point on my graph, so I want to connect those two things. Okay. Then notice we go from this point to this point. It doesn't really matter how high or how low you go because we are sketching. But you would go up and somehow turn around and come back to that point. And after you hit that point, notice that the highlighting's down here, so you have to go below. Okay? And you wouldn't be able to follow this asymptote up, you'd follow it down, so you would want to connect some behavior like this. Now, on the far right side, you know that you would want to be at this portion of the asymptote, not over here because of the highlighting. And again, this horizontal asymptote is describing to us the end behavior. We want it to look like it's flat at 1.5 at the ends. So I want to connect something that shows those behaviors. And then lastly, you guys have to list the domain and range. So I am going to use the little technique I talked about last time. I'm going to kind of mark each one on a y-axis for myself. So this first one right here goes up infinitely. It comes down to the horizontal asymptote, which is at 1.5, but never actually touches it. So at 1.5, it's like it has an open point, like it didn't quite touch that, but everything above it. This second piece right here that almost looks kind of like a parabola with this weird non-symmetry to it, came up to like 1 on the graph and seems like it hits 1 the way I drew it. So yours could be a little bit different depending. So it seems like it hits 1 on my graph and covers everything below that. And then the third piece, it's kind of like the first piece. It goes up towards infinity and it does come down right about to 1.5. So again, it would have that open point at 1.5 and all the points above it. And then see how there's like this gap in the middle? This means that you need to list 2 things for your range, 2 different pieces. So for your range in this case, for this part down here, you would call this y is less than or equal to 1. That's what this graph represents. Then you can just say or, and then you want to write what this piece represents here, and this would be y being greater than 1.5. For the domain of the function, which x values did we skip over? Our vertical asymptotes are marking that. And so we would say you cannot include x's, or x cannot equal -1/2 and 3. So let's look at one more of these. Remember, we're skipping C and D because those will have oblique asymptotes. And we're going to go down here to part E. And the first thing that we're going to do is rewrite it in its most factored form. If you need help with factoring, message me and we can go back through some of that stuff. So this is what it looks like. And notice we have something that does cancel in this case, giving us a much simpler equation, which hopefully means we have less things we have to test and mark and stuff like that. Now, as we make our list of information, though, the fact that something canceled was very important. So remember, we have, for the category of asymptotes, vertical asymptotes, horizontal and oblique. Remember, you have one or the other of these. Then we have holes. And then for our intercepts, we're looking for x-intercepts and y-intercepts. So the fact that this canceled out means that we do have a hole. Now you have to remember how we find the hole. If you remember how this works, what we're doing is first asking ourselves, that factor that you canceled out, what x value would make it equal to 0? So we're kind of going, when would x minus 5, that's what I canceled out, equal 0? And the answer to that is 5. So what you've just found out is that your hole is at a point on the graph where 5 is the x. And then you guys know how it normally works. In order to get a y coordinate, we plug in an x coordinate, in this case to the simpler version of the equation. So we're going to take the new simpler version of the equation, and we're going to plug that 5 in, and we're going to calculate what we get for y, which is 1/8. So we'll mark that on the graph in a little bit. We're actually going to mark that point. It will actually help you. It's like you have one extra point on your graph, even though it's really skipping over that point. Okay? Now we can look at the new version of the equation to answer everything else on here. So notice that the degree of the denominator is higher, which means no oblique asymptote. And it means not only do you have a horizontal asymptote, but your horizontal asymptote is at 0. For our vertical asymptote, we're going to set the denominator equal to 0. And we get one vertical asymptote in this case at x equals -3. And now we're going to look to find our x-intercepts and y-intercepts. So for our x-intercept, remember how we like to solve these? Multiply both sides by that factor in the denominator. And on the left side, it's still 0. On the right side, those cancel out. And this is unique. You know, there's no x left to solve for, and this doesn't make sense. So this equation has no solution. And remember, this equation was to help you find x-intercepts. So if there's no solution to the equation that helps you find x-intercepts, then you don't have any x-intercepts. And then our y-intercept, we're going to take the new version of the equation. Everything is done with that new version, and plug in 0 for x. That gives us 1/3 for y. And so we do have a y-intercept. So like usual, we're going to go mark all this information on the graph. So vertical asymptote at x equals -3. And horizontal asymptote at y equals 0. And we have a hole at 5/1/8. So holes are interesting because it's telling us what's not there, but we actually get to plot where the graph would normally go. So I'm going to +5, +1/8, which would be very close to the asymptote. So I know the curve is going to be at that point, but I'm just indicating that we will technically be skipping over that one point. And then we have a y-intercept of 0, 1/3. And now we're going to go through and we're going to test our values to try and get pieces of this graph. So the good news here is, notice that when we draw our analysis of the x-axis, we have a vertical asymptote at -3. But other than that, we don't have any x-intercepts or any other vertical asymptotes. So we really only have 2 sections to test here. What happens when x's are smaller than -3 and what happens when they're bigger. Okay, so that will mean a lot less testing this time, which will be helpful. So remember, what we're testing them in is this version of the equation that's 1/x + 3. And so the first thing I'm going to do is test numbers smaller than -3. So let's say I choose -10. Then I would be plugging it in like this. And so 1 will always be positive. -10 + 3 is negative, and a positive divided by a negative will be negative. So when you plug in any x smaller than -3, you're getting a y value that's negative. And then if we try it for something bigger than -3, like 0, we get a positive divided by a positive, which means for any x is bigger than -3, we get a positive. And again, I'm going to go back to that highlighting. If you don't like it, don't use it. If it helps you, then go ahead and use it. So a negative here means I can only graph below the x-axis in this portion where x is smaller than -3. When x is on the other side of -3, I can only graph above the x-axis. And then remember the things that are here to guide you. This horizontal asymptote at 0 is telling you at the end of the graph you need to lay flat like 0 on both sides. And then the vertical asymptote, you know that as you get close to it, you either curve and go up along it or down along it. So in this first area, I cannot go upward because of where my highlighting is, that I'm only allowed to use negative y values. On the other side of the asymptote, I must be going up because those are where positive y values are. And I can't graph negative y values. So I'm just literally going to connect a curve that looks like it gets very close to 0 and follows this downward. And on the other side, the same thing. I'm just going to make sure I cross through those points that I know exist. There we go. And then for the domain and range, I'm going to use that y-axis kind of analysis to help me figure out my range here. So for this curve, it goes down towards -infinity and it comes right up to 0 but doesn't touch it. So it would have like an open point at 0 because it doesn't actually hit 0, and everything below 0. This other curve here is above 0 and not hitting 0. So it would kind of look like this, except for there is a hole. So what y value is that hole at? The y value of our hole was 1/8. So it's like it's missing this little y value at 1/8. Okay. Now, this basically means we don't hit 0 and we don't hit 1/8. Because it's just two specific numbers, I'm going to write the range in this case the same way that we were writing the domain. I'm just going to say y cannot equal 1/8 or 0. Okay. And then our domain here, what x's did we skip? The vertical asymptote was only at -3, but then remember you have a hole. So you technically jumped over this one point, and at that one point the x value was 5. So you need x cannot equal -3, but also